Welcome back. Alright, so we're going to do Chapter 3, Problem 105. Alright, so basically it's asking you I'm going to do Part A. It says determine the apple center and surface temperatures. So initially what I did was set up the problem, and basically we're going to model this as a sphere because those apples are close enough to a sphere. Alright, so I'm thinking that we're probably going to be needing the spherical temperature distribution for this. So that is T of R equals the Q dot over R naught squared. Alright, let's minimize. So we're going to minimize U over 6K, or is it 4K? I think the cylinder is 4K. Yeah, cylinder is 4K. Alright. 1 minus R squared over R naught. Alright, and plus the surface temperature. Okay. Alright, so we're going to use this formula for this. And this is the spherical temperature distribution. Alright. And so the first step we did was set up our problem, and then we determine which formula we're going to use. Alright, next we can do instead of a thermal circuit this time, let's do a energy balance around this sphere. Alright, and so basically what we're going to have is energy generated, and we'll draw a little control volume right here. And the only thing that's leaving is convection. Okay, and the energy generated is always positive. Then you're going to get the convection, since it's leaving the area, must be equal to 0. Okay. Alright, and this is a volumetric energy generation. Alright, so that means we have to multiply this by a volume. So the volume of a sphere is 3 pi r cubed times q dot minus h over T infinity or T surface. I think does it really matter which way it's flowing? That's the real thing. I just want it positive. I'm gonna do T surface, I think. Alright, I think that sounds good. Yeah, we'll do T surface minus T infinity. Alright, and that all must be equal to 0. Alright, so it gave us a weird volumetric number, which is 4,000 joules per kilogram per day. Alright, so we have to convert that into watts per meter cubed. Alright, so let's see. Let's write that out. 4,000. Whoops. Joules kilogram per day. Alright, and they gave us a density. We can use that to get, because we can get meters cubed on the bottom. So that's my initial idea of why, or initial thought of why I think we can use that. Plus it gets rid of the kilograms. Meters cubed, alright. So then we have to get rid of we can get rid of the day to get us joules per second. So 1 day over 24 hours. And then we can do 1 hour. Hour over 3,600 seconds. Alright. And so I probably should write Q dot equals. Alright. Let's do this real quick. 4,000 times 840 equals divided by 24 divided by 36. 38.9. And that will get us joules per second, which is watts per meter cubed. Alright, so we got that, and they gave us the diameter, which is 80 millimeters, but we can divide it and get 40 and then convert it to meters. Alright, so let's do 4 over 3 pi 0.04 cubed times let's see, 38.9 watts per meter cubed. And this is going to be meters cubed up here, so those will cancel out. Minus 7.5, correct? Watts per meter squared Kelvin. Alright. So this will get me, where are you? And then we have to times that by the area too. Sorry. And the area is 4 pi r squared. Right? I think so. Sorry. Yeah, I think it's 4 pi r squared. 4 pi r naught squared. Then T surface minus 5 degrees C. Alright, so this is 0.04 again. Let's do eraser. Alright, so 0.04 squared. Alright, so we can rearrange all that and get TS. So you just move stuff over. Alright. And so with rearranging everything, let's see. Times that times 0.04 cubed times 38.9. Alright, so that gets me 0.04. Alright, so then we can do that. Alright, so the final answer for that, for the surface, is 5.14 degrees C. Alright. Alright, so there goes that. And now we can plug this back into that formula I wrote down earlier, which is temperature R. Alright, that's a bad R. Equals Q dot R naught squared over 6K times 1 minus R squared over R naught squared plus the temperature surface. Alright? So we're going to use the radius at 0, so T0 equals 38.9 watts per meter cubed times 0.04 squared, alright, over 7.5 watts per meter squared Kelvin. Sorry, watts per meter. I don't know why I said watts per. Oh, no. Sorry. That's thermal conductivity. I even wrote that out and I forgot it. So 0.5 watts per meter Kelvin. Okay. Alright, then 1 minus. That becomes. Alright, that just becomes 1. Let's just. Alright. So you put R squared in there, you get 0, which then you just 1. So times 1 minus 0, we'll put that, that helps, plus 5.41. Alright, and solving that. Alright, so solving that, we get. So basically, then T inside equals 5.26 degrees C. Alright. And I'm not going to do part B because that requires graphing. Alright, I'll see you guys next time. If you have any questions, post in the comments below. Let me know how I'm doing, if I'm going too fast, too slow, something like that. Just want to say hi. Just let me know.